Here we have our JC cracker. This is our more high throughput cracker. We're able to do more pecans in a short period of time. The way this cracker works is you have a hopper here and a vibratory conveyor, and this conveyor shakes and moves the pecans along and dumps them into this machine, which has a large plate that is on cams, and it's impacting the pecans over and over again at a certain frequency, which we can change. Versus the more traditional cracker over here, the Meyer cracker, which has a elevator that's picking up one pecan at a time and cracking it longitudinally. Right now we're working on our full factorial experiment for essentially characterizing the JC cracker, and we're trying to find the machine parameters that ultimately put out the highest half yield, and we're also working to classify the different types of cracks that the different machine parameters put out. One of those machine parameters that we're focusing on, our independent variable, which we're going to change throughout our experiment, is throughput. Throughput is a number that we back calculated from industry. We looked and saw what they were putting through their machines, and then we calculated 75 and 50% of that rate. And our goal was to replicate that here on our machine. Basically, we want to recreate the throughputs we're seeing in industry, and that involves changing the power unit here on this control box so that we're seeing the same, originally it was pounds per second of pecans coming through this conveyor as they do at the processor. In doing so, we found that shell moisture and the surface dynamics of shell moisture moving down this conveyor as it was vibrating had significant impact on your throughput. We found this out because one day when we were trying to connect the power units here with the throughput numbers, we had to stop for a demonstration for about 30 minutes. So those pecans had about 30 minutes to sit there and dry. When we picked up at the same power unit, we found that our throughput had changed pretty dramatically. We realized there was something there. We said, okay, maybe shell moisture has a significant effect on the weight. And so we went through and we measured, and we saw that there was not a huge difference in weight, and that most of the weight was carried in the kernel, but kernel moisture drops by only 1% over about 24 hours. That led us to the conclusion that it was probably something to do with the surface dynamics of these pecans and how fast the shells themselves dry. From there, we realized we wouldn't be able to run an experiment and maintain constant throughput without some sort of alternative method, and so we moved towards a control system. Control theory is a part of electrical engineering that maintains a desired set point despite any noise being introduced into the system. So in this case, our noise is the shell moisture drying over time. That's something we can't control, and the controller that we programmed is compensating for that. For every control system, you need a sensor. We started off by trying to use a LiDAR sensor. A LiDAR sensor is essentially a laser, and we had it on a little motor, and it would spin and tell us the distance of each point it was measuring around the circumference of this motor. We tried to count the pecans by essentially making a point map of the surface of the conveyor. Unfortunately, that sensor did not spin fast enough, so we decided to move to a object detection computer vision model. Here we have a camera that's connected to our Linux computer right there, and basically what's happening is we've trained a computer vision model to count the number of pecans that are moving through this conveyor at a time. Here's a demonstration of what it looks like for our computer vision model to be running and counting pecans. So here you can see a visualization of what's actually happening in our computer vision model. Once it reaches a certain point in the frame where we know each pecan is going to be fully in the frame, it counts them, and we have a clock running in the background that's basically telling the computer how many pecans per second it's seeing. After this camera here sends the footage to the model, it then puts out a pecans per second measurement, which is then filtered because pecans are very discrete sizes and different shapes, through a common filter and sent into our control system, which is then adjusting the outputs on this conveyor accordingly. We've optimized our control system such that at our lowest throughput of 13 pecans per second, we're seeing a steady state error of less than 0.8%. And at the worst case scenario of 38 pecans a second, we're seeing 0.5% steady state error. That is much lower than the acceptable threshold of 5% steady state error, which we're very happy with. So here we have a different vision model that we're working on. Unlike this one over here that we had for feed rate control, this one is a segmentation model. So basically, as the pecans work down this conveyor, this computer vision model is going to be the exact shape of the cracked portion of the pecan and then also the uncracked portion of the pecan. The goal is to run that data into some sort of numerical model that allows us to have consistent classification metrics for each of these pecans. And ultimately, the goal of being able to classify pecans is that it's an extra data point as we go into the sheller here that will enable us to maximize our half yield numbers once they work through the sheller and onto the blower. A point of emphasis for our project has been to work on getting precise control of this machinery. When we got most of this machinery, everything had to be adjusted by hand. Basically, it was left to the operator's opinion on where different settings, different levers and such needed to be. Now we have, we've implemented things such as here on the JC, we have a servo that can change the height of the plate that is impacting the pecans. With this, we can precisely change that relative height of the plate, giving us more precise control of the cracking dynamics within the machine. Also, as mentioned in a previous video, we have full control of the feed rate of this conveyor here using a computer vision model. There's other things such as here on the sheller. What you see in industry is a single speed motor that spins both the drum and the paddle shaft at the same RPM. However, we've adapted a motor that is capable of spinning the drum and paddle shaft at independent speeds, and we can choose a wide range of different RPMs. We've also added a few quality of life things to these equipment, helping the workers see what's going on in our operation and also catering to their safety. So here you see we've added a plexiglass shielding around the sheller here. This allows the operator to see what's going on inside, but also stay safe, and there's no way he could get caught up in any of the machinery here. And then in all of our hoppers, we have a little window there for allowing us to see how many pecans are in the hopper. At the beginning of our process here, we have our storage. We have limited space, so we kind of have to coordinate whatever pecans are going to be used sooner. We can leave outside the fridge, but anything that's going to be used in longer than a few days, we got to make sure to keep it inside the fridge just to maintain kind of the same standard that you would see in industry. So research shows that conditioning pecans in water before putting them through the cracking and shelling process increases your half yield numbers. So here we've recently moved from conditioning pecans in small bins like this to actually conditioning what we call large bath pecans. We just use water out of the tap. In the future, we have a couple of projects that we're looking at, such as negative pressure conditioning. But for right now, this is the method that we use here. From conditioning, been playing with air drying time because of how we've seen pecan shell surface dynamics have changed things within the cracking process. This is an independent variable that we've recently introduced. We have trays here with little grates in them. This isn't something that is standard in industry. There is a certain amount of time that they spend on conveyors, but they don't purposely let the pecans sit and dry for some time. There's some food regulation aspects to that limit how long you can let them sit for. We're just seeing how far we can push that to maybe increase half yield later on. After they air dry for some time, we then move and put them into the cracker. This cracker here is the JC cracker. It cracks pecans radially, so along, I guess, what you'd call their sides. This is our high throughput piece of equipment here. It takes pecans in this hopper, moves them along this vibratory conveyor here, and then drops them off in large numbers through this machine, where it has plates here that are essentially the width and length of the machine that are impacting the large batches of pecans as they flow through here. Another piece of cracking equipment we have here is the more traditional piece of equipment that has been used in industry for over 50 years, called the Meyer cracker. This is a much lower throughput piece of equipment, but has higher precision, and it cracks the pecans axially. So it has a little elevator here that picks up the pecans one at a time, and it brings them through the machine there, and there's a piston that impacts each pecan and then drops it off onto our conveyor. And then this conveyor goes over here to our bucket elevator, where it's then brought up and dropped off into a hopper over the sheller. The pecans are then moved through the sheller, where they're spun on a drum that is contacting another shaft with paddles on it. And it's basically, the intent of this is to separate the shell and the kernel. Most of the product ideally drops down into these bins, the shells and the kernels, and whatever doesn't get dropped down there kind of falls into this outlet here, and we recycle it back into the machine. So this piece of equipment here is called the blower. Basically, the product that comes out of the sheller, the shells and kernels, are dropped in here, and ideally vibratory conveyor takes these into this inlet here, and the blower here at the bottom blows the shells up here and down and out into a separate bin, and the meat of the pecans falls down into the bottom here, where they're then separated. Recently we've been trying to implement RFID throughout our whole system here. What RFID does is it essentially lets us give a batch of pecans an ID and follow it through the whole process. So we will have full telemetry of our system here. Here we have an example of one of our implementations of RFID. This is our station where, once the pecans have gone through the whole process and we've separated them from the shells, we want to actually measure the half yield numbers. Half yield is the percent weight of the entire batch of the meat of pecans that is halves. Here's an example of implementation of RFID on one of the stations of our pecan process here. You want to be able to take a sample and measure the half yield. This is a general sample, so it's halves and pieces. So we'll take and we'll put our little RFID reader up here to the general yield sample mode. Then you'll take the reader right here and you'll put it up to the bottom of the cup, and you'll see it says 7 right there on the screen now. This is cup 7. You'll throw the cup in the scale here, and then here in a second the weight will pop up. So here you can see the numbers come up now, and then what we would do is take our sample here, dump it out, and we'd separate all the halves from the sample. We'd go in and we'd scan the tag that says halves only. You can see it's switched to half yield sample here. Again, scan the cup, and we'll throw it on the scale once more. Now you can see here, this is our sample weight for the half yields. So here's our Steinlight moisture meter. Basically, one of the independent variables we've been focusing on for our experiments here is kernel moisture. And so we'll collect here a 150 gram sample of whole halves, and we'll take here and we'll dump them in this little hopper, and you go and you drop it in there, and you wait a second. Just thinking here. You see here, this batch of kernels is 7.5% moisture, and so then you just drop it out. It falls in the bottom here into this tray, and we would recycle it. So basically the way this machine works is It measures the electrical resistance of these pecans and then back calculates the percent moisture based off of the calibration tables.